Before we see the solution, let's fully appreciate the problem. Imagine tracking just 5 high scores. You'd need int score 1, int score 2, int score 3, and so on. This approach, known as using scalar variables, is clumsy, error-prone, and impossible to scale. If you needed 1,000 scores, your code would be a disaster. This limitation is precisely why arrays were invented. The elegant solution is the array. An array is a data structure that stores a fixed size, sequential collection of elements, all of the same data type. Think of it as a single, named container with multiple numbered compartments. This structure allows us to manage a whole set of values using just one name, bringing order and efficiency to our code. Let's look at the 3 core properties that define an array. The first core property is that arrays have a fixed size. When you create an array, you must tell the compiler exactly how many elements it will hold. This size is determined at compile time and cannot be changed while the program is running. This static nature is a key characteristic of C arrays and is fundamental to how they manage memory. The second property, and the secret to their speed, is that arrays are stored in a single, unbroken block of memory. This is called contiguous memory allocation. Each element sits directly next to the previous one, with no gaps. This perfect organization allows the computer to calculate the exact location of any element instantly, which is why accessing data in an array is incredibly fast. The third and final core property is that arrays are homogeneous. This simply means all elements in a single array must be of the exact same data type. You can have an array of integers, an array of characters, or an array of floats, but you cannot mix them. This rule ensures memory consistency and predictable behavior for every element in the collection. Now that we understand what an array is, let's learn how to create one. This process is called declaration. The syntax is straightforward. You specify the element data type, give the array a name, and state its fixed size in square brackets. For example, int highscores 5 tells the compiler, reserve a contiguous block of memory for 5 integers and name it highscores. A crucial point about declaration: if you declare an array but don't give it any initial values, what's inside it? The answer is garbage values. The memory is reserved, but it contains whatever random data was left over in that memory location. Using these garbage values can lead to unpredictable bugs. This is why initializing your array is so important. To avoid garbage values, we should initialize our array, which means giving it starting values. The most common way is to provide the values in a comma-separated list inside curly braces right at declaration. For example, int highscores 5 equals 98, 95, 92, 88, 85. Both declares the array and fills it with our specific scores in one clean step. But what if you provide fewer values than the array size? For instance, int values 5 equals 10, 20. C handles this predictably. It fills the elements you specified and then automatically initializes all remaining elements to 0. This is a very useful feature, guaranteeing that the rest of your array is clean and not filled with garbage. C also offers a convenient shortcut. If you provide an initializer list, you can omit the size in the square brackets. The compiler is smart enough to count the elements for you. Writing int items square brackets 100, 200, 300 automatically creates an array of size 3. This is a great way to prevent mistakes where your size and your initializer list don't match. With our array created and filled, how do we get to a specific element? We use an index. This is the most critical concept for using arrays. C is 0 indexed. This means the first element is at index 0, the second at index 1, and so on. For an array of size n, the valid indices are always 0 through n-1. Forgetting this is a classic beginner mistake. To read a value, we use the array name followed by the index in square brackets. For example, int second score equals high scores brackets 1 accesses the element at index 1, which is our second score, reads its value, 95, and copies it into the second score variable. This bracket notation provides direct, high-speed access to any element in the collection. Writing to an array works the same way. If we wanted to update the fourth score, we'd write high scores 3 equals 90. This targets the element at index 3 and overwrites its current value. The original value of 88 is permanently replaced with 90. This allows us to modify our data collection dynamically as our program runs. Accessing elements one by one is fine, but the real power of arrays is unlocked when we combine them with loops. A for loop is the perfect tool to iterate through an array, performing an action on every single element. By using a loop counter that goes from index 0 up to size -1, we can automate processing for arrays of any size. Let's see a practical example, calculating the average of our high scores. First, we'd use a loop to sum all the elements. We initialize a sum variable to 0, then loop through the array, adding each high scores I to the sum. After the loop, sum holds the total. We can then divide by the size to find the average. This is a classic and powerful array algorithm. Now for a critical warning. What happens if you try to access an index that doesn't exist, like high scores 5 in our size 5 array? This is called an out-of-bounds access. C does not prevent this. Instead, it leads to undefined behavior. Your program might crash, corrupt data, or even create a security vulnerability. It is your responsibility as the programmer to always stay within the valid index range. So how can we write safer code, especially if we don't know the array's exact size? C provides the sizeof operator. Sizeof high scores gives the total memory size of the entire array in bytes. By dividing this by the size of a single element, size of high scores 0, we can reliably calculate the number of elements. This is the standard, portable way to make your loops adapt to the array size. Now let's move to a more advanced topic using arrays with functions. When you pass an array to a function, C does something very efficient. It doesn't copy the entire array. Instead, it just passes the memory address of the first element. This is known as passing a pointer. This is extremely fast, especially for large arrays, but it has a very important side effect. The side effect is that the function works directly on the original array's memory. If the function modifies any element, that change is permanent and will be visible back in the calling function. For example, if modify scores changes an element to 100, the original high scores array is changed. This is powerful, but you must be aware that the function can alter your original data. There's a tricky gotcha here. When an array is passed to a function, it decays into a simple pointer. This means the sizeof trick we just learned will not work inside that function. Sizeof on the function's parameter will just give you the size of a pointer, not the whole array. Therefore, the standard professional practice is to always pass the array's size as a separate argument to the function. So far, we've only seen one-dimensional arrays, which are like simple lists. But C can handle more complex structures. A two-dimensional array can be visualized as a grid or a table with rows and columns. This is perfect for representing things like a chessboard, a spreadsheet, a tic-tac-toe board, or the pixels of an image. Under the hood, a 2D array is still stored as one single contiguous block of memory. C lays it out in row major order, meaning it stores the first complete row, followed by the second complete row, and so on. Understanding this memory layout is key to understanding how the compiler finds an element like matrix 1, 2 so quickly. To access an element in a 2D array, you must provide two indices. the first for the row and the second for the column, both zero-based. So in our matrix 3, 4, matrix 0, 0 is the top left element, and matrix 1, 2 would access the element in the second row, third column. This two-index system lets you pinpoint any cell in the grid. Just as we use one loop for a 1D array, we use two nested loops to iterate over a 2D array. The outer loop typically iterates through the rows, and for each row, the inner loop iterates through all its columns. This pattern allows you to systematically visit every single cell, for example, to initialize a game board or process every pixel in an image. Finally, we arrive at a fundamental concept in C. Strings are arrays. A C-style string is nothing more than an array of characters. When you write hello, you are creating an array of characters. But there's one special rule that makes it a string. It must end with a special null-terminator character. This special character is the null-terminator, written as 0. The compiler automatically adds it to the end of any string literal. So, the string hello actually takes up 6 characters of memory: H, E, L, L, O, and the final 0. This null-terminator is essential. It's how C functions like printf and string_len know where the string ends. And that concludes our masterclass on C arrays. We've journeyed from the fundamental problem of managing data through the core properties, declaration, and initialization. We mastered indexing, iteration with loops, and learned how to handle arrays safely with sizeof. We explored advanced topics like how arrays work with functions, the structure of 2D grids, and finally, the deep connection between arrays and strings. You now have the complete toolkit for using arrays effectively.